Okay, let's dive right into this. Welcome back to another explainer. Today, we're taking a structured look at the absolute foundation of digital communication. Look, if you're a software engineer, an intermediate tech enthusiast, or maybe a junior dev trying to make sense of the invisible plumbing that literally makes the internet work, well, you are in exactly the right place. We're going to unpack the architectural blueprints of the 7-layer OSI model, and we're going to do it from a highly practical, developer-centric perspective.
But before we even touch the layers themselves, we really need to establish the massive problem this model was built to solve. I mean, think about it. How do billions of completely different devices actually understand each other? You've got an Apple smartphone on a cellular network in Tokyo talking seamlessly to a Linux server sitting in an Amazon data center over in Virginia. They use totally different hardware, entirely different operating systems, and totally different code bases. Without a universal, incredibly rigid set of translation standards, the internet as we know it simply would not exist. It would just be localized islands of tech. The OSI model is the universal Rosetta Stone that bridges that gap.
So, here's our roadmap for today. First, we'll decode the overall OSI structure. Then, we'll move top-down through the software layers, hit the transport heart in the middle, dive into the hardware layers, and finally, follow the complete data journey.
All right, Section 1, Decoding the OSI model, focusing on structure and standardization.
Now, what's really interesting here is that understanding the structure is an incredibly pragmatic tool. When an API call randomly fails or a website just won't load, knowing this architectural blueprint tells you exactly how to isolate your bugs systematically. So here is the open systems interconnection model laid out perfectly. Now, it's usually taught from the bottom up, but since we're looking at this from a software engineer's perspective, we're going to go top down. At the very top, layer 7 is the application layer. Then 6th, presentation. 5, session. 4, transport, 3, network, 2, data link, and finally, down at the absolute bare metal, layer 1, physical. Try to keep this stack in your mind's eye as we go, because literally every single byte of data you have ever sent over a network has traveled through this exact sequence. Moving on to Section 2, layers 7 to 5. These are the software layers, often called the host layers.
Starting top-down really is the most relatable starting point, because honestly, this is where developers spend almost all of their time. We collectively call these top 3 the host layers. They're entirely responsible for application-level data formatting, encryption, and maintaining the communication session. If we use the shipping department assembly line analogy, the host layers represent the phase where you are actually writing the letter. You're deciding what the message says, translating it into a language the recipient can read, and then stuffing it into an envelope. This all happens strictly on the sender's computer, completely oblivious to the physical network outside. Breaking those host layers down specifically, we start right at layer 7, application. This is where your web browser or your email client lives. It's your direct interface with the user. Next, your data drops to layer 6, presentation. Think of this as your translator. It takes that application data and converts it into a standard format, like JSON or XML. And crucially, this is also where encryption happens. If you're using HTTPS, your data gets scrambled into unreadable ciphertext right here at layer 6. Finally, we hit layer 5, session. You can think of this layer as the event coordinator. It opens the line of communication between two devices, keeps it open while the data is actively being exchanged, and then properly terminates the session when the conversation is officially over. These 3 layers prepare your data perfectly before it even considers leaving the building.
Next up, Section 3, layer 4, the transport heart. And this brilliantly illustrates the exact moment our data transitions from high-level software abstractions down toward network reality. Once the data is perfectly formatted and encrypted, it drops down to layer 4, which is the critical middleman. This layer handles reliable data delivery, error checking, and segmentation. Going back to our shipping analogy, your letter is written, it's in the envelope, now the shipping department has to make a choice. Do we send this via certified mail where we require a signature upon delivery, or do we just send it standard delivery and kind of hope it gets there? In networking, certified mail is TCP. It guarantees delivery and rigorously checks for errors, which is absolutely great for loading a web page or securely sending a file. Standard delivery, on the other hand, is UDP. It's lightning fast, but it doesn't guarantee every single packet arrives. That's actually perfect for live video streaming, where speed matters way more than perfection. Layer 4 also chops your massive piece of data into smaller, manageable chunks called segments.
All right, Section 4, layers 3 to 1. The hardware or the media layers.
Now that a delivery method is officially chosen, we leave the software realm behind us. We're now looking at how data physically traverses the external world.
These bottom three are collectively known as the media layers, and they're focused entirely on global network routing, local switching, and the actual physical transmission of your data over wires, fiber optics, or radio waves. Now, for my software engineers watching this explainer, when you're debugging and you've meticulously verified your code is pristine, the API is running flawlessly, the certificates are valid, but the system is still somehow down, you've reached the media layers. This is exactly where you stop checking your application code and you start checking to see if someone accidentally unplugged a cable in the server room.
So the crucial point here is understanding the handoff that happens between these next layers, because this trips up a lot of developers. Layer 3, the network layer, handles IP addresses and global routing. Think of an IP address as a zip code on a package. It's a logical address that helps routers navigate your data across the entire globe from network to network. But once your data arrives at the destination's local network, Layer 3 is completely done and hands the baton off to Layer 2, the data link layer. Now, Layer 2 uses MAC addresses, which are actually physically burned into a device's network card. This handles local switching, meaning it moves the data hop to hop across the immediate local physical network to finally reach the exact correct machine. Basically, Layer 3 gets you to the right city, Layer 2 gets you to the correct physical front door. And finally, we hit the absolute rock-bottom foundation of the stack, Layer 1, the physical layer. This is exactly what it sounds like. There are absolutely no IP addresses here. No software, no formatting, just raw, unadulterated bit streams. The ones and zeros are converted into electrical pulses over a copper wire, or maybe pulses of light over fiber optic cables, or even radio frequency waves over Wi-Fi. If Layer 4 was choosing the shipping method, Layer 1 is the literal 18-wheeler truck bombing down the highway carrying your data. Which brings us to Section 5, the complete data journey, focusing on encapsulation.
We've isolated our blueprint, right? But networks are dynamic. We really need to see this model in active motion. The way data actually moves through this stack is through an active process called encapsulation. That's the process of wrapping data with layer-specific headers as it moves down the OSI stack for transmission. It's kind of like a set of Russian nesting dolls. Your original application data is that innermost doll. As it drops down through each layer, that specific layer slaps its own header onto the data, basically its own set of instructions, creating a slightly larger doll. The transport layer adds TCP port numbers. The network layer wraps that up with IP addresses. The data link layer wraps that up with MAC addresses. It's a literal assembly line. Let's see how this builds step by step, because this gives you some incredibly important terminology for your troubleshooting. At Layer 7, 6, and 5, your payload is quite simply called data. But when it hits Layer 4 and gets chopped up with a TCP header attached, we don't call it data anymore. We call those segments. Those segments then drop to Layer 3, where IP addresses are added. Now they're called packets. Those packets drop to Layer 2, MAC addresses are attached, and boom, they become frames. Finally, down at Layer 1, those frames are converted into raw bits for physical transmission. Data, segments, packets, frames, bits. If a network engineer ever tells you they're dropping packets, you instantly know you have a Layer 3 routing issue. The terminology points exactly to the layer. Of course, once those bits travel across the physical wire and reach the destination computer, the entire process just simply runs in reverse. This is what we call decapsulation. The receiving machine takes the raw bits at Layer 1, rebuilds them into Layer 2 frames, reads the MAC address to confirm, yep, this is for me, strips that header off, and passes it up to Layer 3. It reads the IP address, strips that header, passes it to Layer 4. It literally unpacks the dolls one by one, moving all the way up the stack until finally, the pure original data is presented seamlessly to the application at Layer 7. And honestly, that is the pure brilliance of the OSI model. It takes the chaotic, infinitely complex world of global communication and breaks it down into a neat, standardized 7-step assembly line. But I want to leave you with a provocative thought as we wrap up today. This blueprint was designed decades ago for very traditional networks. Will this rigidly structured OSI model actually survive the next evolution of decentralized peer-to-peer tech? Or the completely mind-bending reality of quantum networking? It's a fascinating challenge to the mental model we just built together today. I highly encourage you to go research how next-gen networking architectures are trying to adapt this classic framework. Thanks for joining me on this explainer, and keep learning.